Is it possible that the grandest story we have ever told ourselves, the epic of our cosmos from the Big Bang to the present day, is merely the opening chapter of a much larger, more bewildering narrative? We have spent centuries gazing into the abyss, charting the heavens and meticulously assembling a portrait of our reality. It is a picture of staggering scale and breathtaking beauty, a universe of 100 billion galaxies each, a spinning city of 100 billion stars all adrift in an expanding sea of space-time. This is our home. This we believed was everything, a singular magnificent creation, a universe so vast that to comprehend its edges is to grapple with the very meaning of infinity. But what if this perception, this feeling of ultimate grandeur, is a profound illusion? What if the entirety of our known existence, every star, every planet, every living thing, is nothing more than a single fragile bubble floating in an endless, churning foam of other universes? This is the precipice upon which modern cosmology now stands, peering into a theoretical abyss that makes our own cosmic horizon seem as quaint and familiar as our own backyard. The idea is so radical it borders on blasphemy, yet it emerges not from fiction, but from the deepest, most successful theories we have about the birth of our own reality. It suggests that the Big Bang was not a unique event, a singular spark that ignited all of creation. Instead, it posits that our cosmic birth was just one of countless flashes in an eternal, self-perpetuating cosmic engine, a process called eternal inflation. This engine, a runaway expansion of space-time itself, is constantly giving birth to new universes, each one a self-contained bubble of space and time, with its own unique set of physical laws, its own constants of nature, perhaps even its own dimensions. Our universe in this staggering vision is but a single droplet in a boundless cosmic ocean, a single note in an infinite symphony. Before we can leap into that ocean, we must first appreciate the shores from which we depart. For a century, we have meticulously mapped our own cosmic island. We learned that the faint milky smudges in our telescopes were not clouds of gas within our own Milky Way, but were in fact entire other galaxies' island universes as large as our own, separated by gulfs of darkness so immense that light itself, the fastest thing we know, takes millions of years to cross them. With instruments like Hubble and the James Webb Space Telescope, we have peered back in time, gazing at galaxies as they were over 13 billion years ago, ghostly infant structures coalescing in the dawn of cosmic history. We have traced the architecture of this cosmos, discovering that galaxies are not scattered randomly. They are woven into a magnificent luminous tapestry, a cosmic web of filaments and clusters surrounding vast, empty voids, a structure of unimaginable complexity sculpted by the gentle but relentless pull of gravity over eons. We have listened to the universe's oldest light, the faint residual afterglow of the Big Bang itself. This is the cosmic microwave background, a faint radio hiss that permeates all of space, an echo of a time when the entire observable universe was a hot, dense, opaque fireball. Imprinted upon this ancient light are the seeds of all future structure, tiny fluctuations in temperature, infinitesimally small variations in density, that over billions of years would be magnified by gravity to become the great superclusters of galaxies we see today. This light tells a powerful story of our origins, a story of a universe that began in a state of nearly perfect uniformity and has been expanding and cooling ever since. It provides the bedrock of our modern cosmological model, a testament to our ability to decode the universe's most ancient secrets. From this evidence, we have built a coherent, powerful, and deeply tested history of our cosmos, a timeline stretching from the first fractions of a second after the Big Bang through the forging of the first stars, the formation of galaxies, the birth of our sun, and finally to this very moment as you watch this, a fleeting instant in the life of a 14 billion-year-old universe. It is a complete and triumphant story. It feels final. It feels like we have found the edges of the map. And yet, if you look closely at this beautiful picture we have painted, you begin to see subtle cracks in the canvas. There are features of our universe that are so strange, so improbable, that they seem to cry out for a deeper explanation. They hint that our magnificent self-contained cosmos might not be the whole story. These are the cosmic coincidences, the pieces of the puzzle that don't quite fit the unsettling clues that suggest our reality. might be part of something far, far larger. The first great mystery is one of exquisite balance. The physical laws that govern our universe appear to be precariously fine-tuned for life balanced on a knife's edge of cosmic chance. Consider the force of gravity. If it were just a tiny fraction stronger, the universe would have collapsed back in on itself moments after the Big Bang, long before the first stars could ignite. If it were a tiny fraction, weaker galaxies and stars would never have formed at all. Matter would have dispersed too quickly, leaving behind a cold, thin, featureless soup of gas. Or look at the force that governs the atom's nucleus. A slight change in its strength and stars, like our Sun, would be unable to forge the carbon, oxygen and iron that are the very building blocks of planets and of life itself. But perhaps the most shocking example is the energy of empty space itself, a value known as the cosmological constant. Our theories predict this value should be enormous, about 120 orders of magnitude larger than what we observe. If it were that large, its repulsive force would have ripped the universe apart at the seams before it even had a chance to form. The value we actually measure is perplexingly impossibly small. It's just enough to be causing the universe's expansion to gently accelerate, but not so much as to prevent the formation of structure. The odds of this value arising by sheer chance are staggeringly low, a number so close to zero it is functionally indistinguishable from it. It's like finding a single specific atom out of all the atoms in a million known universes. It's like throwing a dart from one end of the cosmos to the other and hitting a bullseye 1 millimeter wide. Why is our universe so perfectly, so improbably suited for existence, for complexity? For us, one possible answer is that we simply got lucky. That this is the one and only universe and we just happened to win a cosmic lottery with odds that defy all comprehension. To many physicists, this explanation feels deeply unsatisfying. It feels less like a scientific answer, and more like giving up on the question. It invokes sheer dumb luck as a fundamental principle of creation. There is another even more profound mystery baked into the very geometry of our cosmos. According to Einstein's theory of general relativity, mass and energy curve spacetime, the universe could have been born with any amount of curvature. It could have been shaped like the surface of a sphere, a closed universe that would eventually stop expanding and collapse. Or it could have been shaped like a saddle, an open universe that would expand forever, its contents growing ever more distant and dilute. Instead, our universe appears to be almost perfectly flat. On the grandest scales, we can measure its geometry as Euclidean, just like the geometry you learned in school. To achieve this flatness is an act of incredible cosmic precision. The universe's initial density at the time of the Big Bang had to be tuned to an accuracy of 1 part in 10 to the power of 60. That's a decimal point followed by 60 zeros and then a 1. Any deviation, and the universe would have either collapsed or flown apart long ago. To visualize this, imagine balancing a pencil on its sharpened tip. For it to remain standing, its center of gravity must be perfectly impossibly aligned. Now imagine that pencil having to stay balanced not for a few seconds, but for nearly 14 billion years. That is the flatness problem. Our universe has remained on that impossible knife's edge for its entire history. Why? Why this specific, highly unstable and utterly improbable geometry? For decades, these cosmic riddles, the fine-tuning of the constants, the flatness of space-time, the uncanny uniformity we see in the cosmic microwave background, were treated as separate nagging problems. They were brute facts about our universe that we had to accept, initial conditions that we simply had to plug into our equations without a deeper understanding of their origin. But in the early 1980s, a revolutionary idea emerged that promised to solve all of these puzzles in one elegant, powerful stroke. This idea was cosmic inflation. The theory of inflation proposes that in the very first fraction of a second after the Big Bang, the universe underwent a period of astonishing hyper-accelerated expansion. In a sliver of time almost too small to imagine, a patch of space far smaller than a single proton swelled to a size larger than a galaxy. This explosive growth would have taken any initial curvature the universe possessed and stretched it out to such a colossal scale that our observable portion of it would appear perfectly flat, just as a small patch on the surface of a gigantic balloon seems flat to a tiny ant living on it. This solves the flatness problem. It also explains the universe's uniformity. The entire observable cosmos we see today originated from a tiny causally connected region before inflation began. When that region expanded, it carried its uniform temperature and density with it, imprinting that smoothness across the sky in the cosmic microwave background. Inflation was a stroke of genius, a theoretical master key that unlocked some of cosmology's most stubborn doors. But this powerful theory came with a truly mind-bending consequence, a prediction so strange and profound that its creators initially resisted it. According to the mathematics, once inflation starts, it is almost impossible to stop it everywhere at once. It becomes an eternal, self-reproducing process. While our local patch of the universe did stop inflating, allowing matter and energy to condense and form the structures we see today, the inflationary field would have continued its violent expansion in the regions beyond our cosmic horizon. Think of it like a pot of boiling water. The water itself represents the inflationary vacuum, a high-energy state of space-time. Here and there, regions of this water cool down and a bubble of steam forms. These bubbles are new universes. Inside a bubble like ours, inflation has ended. The energy of the inflationary field has been converted into the hot soup of particles that we call the Big Bang. A stable, calm, and habitable cosmos is born. But outside the bubble in the vast ocean of boiling water, the inflationary process rages on, relentlessly stretching space-time and creating more and more room for new bubbles to form. Each bubble that nucleates in this cosmic foam becomes a new universe, expanding and evolving in isolation. Our Big Bang in this picture was not the beginning of everything, but simply the moment our particular bubble formed and inflation ended locally. The process is eternal, happening over and over again, creating an infinite fractal-like structure of disconnected universes. This is the multiverse. Not a collection of parallel worlds in the science fiction sense coexisting in the same space, but a vast, perhaps infinite cosmic foam of separate, physically real bubble universes, each one potentially vast or even infinite in its own right, each one a complete cosmos separated from the others by an ever-expanding sea of inflationary space-time. This vision, born from the equations of our best cosmological theories, is almost too vast for the human mind to contain. It reframes our entire existence. It means there could be other universes where the laws of physics are subtly or even radically different. Universes with different fundamental particles, different forces of nature, perhaps even different numbers of spatial dimensions. Some might be sterile, fleeting flashes of reality that collapse in an instant or expand into cold, empty nothingness. But in an infinite collection, sheer probability dictates that some bubbles like ours would have just the right combination of laws and constants to allow for the formation of stars, galaxies, and perhaps life. The fine-tuning problem, that baffling cosmic coincidence that made our universe seem so special, simply dissolves. We don't live in a universe fine-tuned for us because we are lucky. We live in this kind of universe because we couldn't have evolved in any other kind. We are by necessity inhabitants of one of the rare life-permitting bubbles in the cosmic foam. We won the cosmic lottery because there were an infinite number of tickets being drawn. This is a perspective shift as profound as any in human history. We once believed the Earth was the centre of all things, a privileged stage for the human drama. Copernicus and Galileo showed us we were just another planet orbiting a rather average star. Then Hubble revealed that our Milky Way was just one of countless galaxies in a vast, indifferent cosmos. Now we're confronted with the possibility that our entire universe, in all its 14-billion-year-old glory, is just one insignificant bubble in a multiverse of unending creation. It is the ultimate demotion. It is the final step in removing humanity from any privileged position in the cosmos. It redefines what it means to be alone. We may be the only intelligent life in our bubble in our observable universe, but the thought that there could be an infinity of other bubbles, other arenas for life and consciousness to emerge, changes the entire philosophical landscape. The questions this raises are dizzying. If there are other universes, are they forever beyond our reach? Condemned to be mere mathematical ghosts in our theories, could two bubble universes ever collide? And if they did, what would happen? Would it be an event of unimaginable violence, a cosmic cataclysm that would annihilate everything? Or could such a collision leave a detectable signature, a bruise on our sky, a faint anomalous scar in the cosmic microwave background, could we in effect see the shadow of another reality? Is this grand, spectacular idea of a cosmic foam merely a fascinating story, a metaphysical playground for theoretical physicists? Or is it a testable scientific hypothesis? Can we find the evidence, the faint whispers from beyond the edge of our own reality, that would transform this incredible theory into an observed fact? The journey to answer that question takes us to the absolute limits of science, to the very edge of our understanding where we must search for the most subtle clues. The faintest fingerprints of another world imprinted on the fabric of our own. That search for a sign that we are not alone in the grandest sense imaginable is where our investigation must now begin. What if the most important question is not what is in our universe, but what our universe is? For all of human history, this has been the ultimate mystery, a question that whispers at the edge of our consciousness whenever we feel dwarfed by the immensity of the night sky. It's a query born from the fundamental human experience of standing on a shore and wondering what lies beyond the horizon. For millennia, this was purely the domain of philosophers and poets, a thought experiment conducted in the theatre of the mind. In ancient Greece, the philosopher Anaximander dared to imagine the apeiron, the boundless, the infinite, a primordial substance from which all worlds are born and to which they all eventually return. He envisioned not a single cosmos, but an endless wellspring of realities, a conception so radical it bordered on blasphemy. A century later, the atomists Leucippus and Democritus went further. They proposed an infinite void filled with an infinite number of atoms colliding and coalescing by pure chance. In this cosmic dance, they reasoned countless worlds must inevitably form. Some they imagined would be like ours, teeming with life. Others would be barren, misshapen, or populated by creatures beyond our wildest imaginings. For them, our existence was not a miracle of unique creation, but a statistical inevitability in an ocean of possibilities. This idea that we are but one island in an endless archipelago of worlds was so profoundly unsettling, so challenging to the idea of our own special place in existence, that it has been suppressed and championed with equal fervour throughout history. It was this very concept among his many heresies that led the philosopher Giordano Bruno to be burned at the stake in the year 1600. He looked at the stars and saw not distant lights in a fixed celestial sphere, but suns each potentially surrounded by its own family of worlds, its own versions of Earth. He paid the ultimate price for suggesting that the mind of God was not so limited as to create only one reality, but was instead an infinite font of creation, spawning endless variations across an eternal canvas. For centuries, Bruno's vision remained a phantom, a poetic dream without a shred of evidence. It was a beautiful, terrifying idea, but it was not science. Science, after all, deals with the observable, the testable, the measurable. And how could one possibly measure a universe that by its very definition lies beyond our own? The question of other worlds lingered in the quiet halls of philosophy, a tantalizing speculation locked away from the rigors of physics. To even begin to approach it scientifically, our entire understanding of reality first had to be torn down and rebuilt from its very foundations. That revolution began not with a telescope, but with a thought. In the early 20th century, Albert Einstein reimagined the universe. His theories of relativity revealed that space and time were not the rigid absolute backdrop that Newton had envisioned. They were a single dynamic entity, space-time a fabric that could be bent, warped, and stretched by the presence of mass and energy. This was a monumental shift. The stage upon which the cosmic drama unfolded was suddenly an active participant in the play. While Einstein was reshaping our theoretical understanding, astronomers were undertaking a revolution of their own, one that would irrevocably alter our sense of scale. For most of history, we believed our Milky Way galaxy was the entirety of the universe. The faint spiral smudges of light seen through telescopes were thought to be nascent solar systems forming within our own cosmic borders. But in the 1920s, from his perch at the Mount Wilson Observatory, the astronomer Edwin Hubble turned his gaze to one of these smudges, the Andromeda Nebula. Using a new method to measure cosmic distances, he made a discovery that shattered our cosmic solitude forever. Andromeda was not a nearby cloud of gas. It was a staggering 2.5 million light-years away, an entire island universe, of hundreds of billions of stars completely separate from our own. Suddenly, the universe grew by an unimaginable factor. Our galaxy was not the whole story. It was a single grain of sand on an infinite beach. This was the first great demotion the moment we realized our home was just one of countless island universes adrift in a vast dark sea. Yet Hubble's work was far from over. As he systematically catalogued these newfound galaxies, he noticed something utterly bizarre. The light from nearly all of them was stretched, shifted towards the red end of the spectrum. It was the cosmic equivalent of a siren's wail dropping in pitch as an ambulance speeds away. The implication was as inescapable as it was world-changing. These galaxies were not just sitting out there in space. They were all in every direction rushing away from us, and the farther away a galaxy was, the faster it was receding. The universe was not static and eternal. It was expanding. This single observation became the cornerstone of modern cosmology. For if the universe is expanding today, it means that yesterday it must have been smaller, and the day before smaller still. If you could run the cosmic clock backward, all of those galaxies, all of that matter and energy would rush together, converging on a single, infinitely dense, infinitely hot point in the distant past. This was the inescapable conclusion, the genesis moment from which everything we know erupted. It was the Big Bang. The discovery of the Big Bang provided us with a creation story written in the language of mathematics and light. It describes a universe born 13.8 billion years ago from a singularity, a point of unimaginable energy. In the first fraction of a second, it underwent a period of violent expansion, inflating faster than the speed of light, laying the foundation for the vast cosmic structure we see today. As it expanded, it cooled. Energy congealed into matter. Protons and neutrons fused to form the first atomic nuclei. For 380,000 years, this nascent universe was a searing, opaque fog of plasma, a cosmic inferno where light was trapped, unable to travel freely. Then, as the universe cooled further, electrons were finally captured by nuclei, forming the first stable atoms. In that moment, the universe became transparent. Light was set free, and for the first time it streamed unimpeded across the cosmos. That first light is still travelling today, a faint ghostly afterglow of creation that permeates all of space. We call it the cosmic microwave background radiation, and it is a perfect baby picture of our universe, a snapshot of the moment it took its first breath. Yet this picture, this elegant theory, comes with a profound and deeply unsettling limitation. Because the universe has a finite age, and the speed of light is a finite velocity, there is a fundamental boundary to what we can see. There is a horizon. Light from any object beyond a certain distance, roughly 46.5 billion light-years in any direction, simply has not had enough time in the 13.8 billion-year history of the cosmos to reach our telescopes. This observable universe is our cosmic cage. It's not a physical wall in space, but a temporal and informational one. We are enclosed within a sphere of knowledge, a bubble of reality defined not by the edge of the universe itself, but by the edge of what we can possibly perceive. Beyond that horizon, the universe almost certainly continues. Based on the geometry of the space, we can see which appears to be perfectly flat. Most cosmologists believe the universe as a whole is vastly larger than our observable patch, perhaps even truly infinite. And here the ghost of Democritus returns to haunt modern science. If the universe is infinite and it is governed by the same physical laws everywhere, then the game of chance he imagined must be playing out on a cosmic scale. In an infinite space, every possible arrangement of matter and energy must exist somewhere. Out there beyond the veil of our horizon, there would be an exact copy of you reading these exact words. Another version would be making a slightly different choice. And another in an endless tapestry of parallel lives playing out across an impossibly vast stage. This is no longer philosophy. It is a direct logical consequence of our best cosmological model. Our universe might not be the universe. It might only be our universe, a tiny finite bubble of perception in an endless eternal whole. This alone is enough to stagger the imagination, but as we looked closer at the fabric of our own reality, we found clues suggesting that the story was even stranger. We found evidence that our bubble might not just be one region among many, but one creation among many. The clues were not written in the stars, but in the very laws that govern them. As physicists in the 20th century delved deeper into the nature of reality, they uncovered a set of fundamental numbers, physical constants that act as the universe's operating system. These are numbers like the strength of gravity, the mass of an electron, and the speed of light. They are not predicted by any theory. They are simply measured values, the foundational pillars upon which the entire edifice of our cosmos is built. And when scientists began to ask a simple question, what would happen if these numbers were different, they stumbled upon an enigma so profound, it has been called the greatest mystery in all of science. They discovered that our universe is balanced on a knife's edge. Take gravity, for instance. It is by far the weakest of the fundamental forces, but its reach is infinite. If you were to increase its strength by just 1 part in a billion stars would burn through their fuel in less than a year, and the entire universe would have collapsed back in on itself moments after the Big Bang. If you were to make it just a little weaker, matter would never have clumped together to form galaxies, stars, or planets. The cosmos would be a thin, featureless soup of hydrogen and helium eternally cold and dark. There would be no structure, no complexity, no life. Consider the strong nuclear force, the cosmic glue that binds protons and neutrons together inside an atom's nucleus. If this force were just 2% stronger, all the hydrogen in the early universe would have fused into heavier elements. There would be no hydrogen left to fuel the long-lived stars like our Sun. No water could ever form. If it were 5% weaker, protons would repel each other too fiercely to bind together at all. Only hydrogen would exist. No carbon, no oxygen, no nitrogen. None of the elements necessary for life as we know it would ever have been forged in the hearts of stars. The list goes on and on. The ratio of the mass of a proton to an electron, the strength of electromagnetism, the very density of matter in the cosmos, all of them appear to be exquisitely precisely tuned to the exact values needed to permit a universe that is stable, complex, and capable of hosting life. It's as if you walked into a room and found 1,000 dials, each of which had to be set to a value with microscopic precision to make the room habitable, and discovered they were all set perfectly. You wouldn't simply assume it was a coincidence. You would suspect that something was going on. But the most baffling case of all the smoking gun of this cosmic fine-tuning is a number called the cosmological constant. This is the value representing the energy of empty space itself, the dark energy that is currently driving the accelerated expansion of our universe. When physicists try to calculate what this value should be, based on our best theories of particle physics, they get a number that is astronomically large. Yet when astronomers measure its actual value, they find a number that is incomprehensibly small. The discrepancy is a 1 followed by 120 zeros. It is without exaggeration the worst theoretical prediction in the entire history of physics. If the cosmological constant were as large as theory, suggests its repulsive force would have been so overwhelming that it would have ripped the universe apart in the first femtosecond of its existence. Atoms would have been torn asunder before they could even form. For stars, galaxies, and planets to have ever had a chance to coalesce, this value had to be almost but not quite zero. The universe, it seems, is not just fine-tuned for life. It is fine-tuned with a precision that makes winning the lottery every day of your life for 1 billion years look like a dead certainty. We are left with a cosmic puzzle that presents us with 3 deeply uncomfortable possibilities. Perhaps it's all just an extraordinary brute force coincidence. We simply won an unbelievable cosmic lottery, and there is no deeper explanation. To many scientists, this is intellectually unsatisfying, a surrender in the face of mystery. Or perhaps these values were deliberately chosen by a creator, a divine fine-tuner, who set the dials of physics with the intention of bringing forth a life-bearing universe. This is a powerful and ancient answer, but it lies beyond the realm of scientific inquiry, a matter of faith rather than testable hypothesis. But a third possibility has over the past few decades emerged from the fringes of theoretical physics into the mainstream. It is an idea as grand as the one for which Bruno was martyred. What if there isn't just one set of dials? What if there are countless universes, a vast churning cosmic foam of bubbles, and in each and every bubble, the fundamental constants of physics are different? In one universe, gravity is strong and it collapses in an instant. In another, the nuclear force is weak and it remains a sterile void of hydrogen. In nearly all of them, the cosmological constant is huge and they tear themselves apart before they are born. In this grander scheme, it is no longer a surprise that we find ourselves in a universe with this specific life-permitting set of laws. We could not by definition exist anywhere else to observe the outcome. We are simply living in one of the rare hospitable bubbles that by pure chance got the physics right. This fine-tuning paradox, this ghost in the machine of the cosmos, has transformed the multiverse from a philosophical daydream into a compelling, perhaps even necessary scientific hypothesis. It suggests our universe is not the product of a single unique event, but the result of a far grander creative process. The evidence on this cosmic crime scene demands a new kind of explanation, one that could emerge not from speculation, but from the very physics of the Big Bang itself, from a theory of cosmic inflation. But what would it mean if the engine that ignited our universe never truly shut down? And so, the greatest story we have ever told ourselves, the story of a single explosive genesis, begins to feel incomplete. To think of our Big Bang not as the ultimate beginning, but merely as our beginning challenges the very foundations of our cosmic perspective. Yet this breathtaking, almost heretical idea does not spring from fantasy. It emerges unbidden from the most rigorous and successful theories we have ever conceived to describe our own reality. The path to these other worlds begins by looking deeper into the crucible of our own, into a moment of creation so violent and so brief, it almost defies imagination. To find the multiverse, we must first return to the first trillionth of a trillionth of a trillionth of a second of our own universe's existence. Our standard model of the Big Bang, for all its triumphs, was haunted by ghosts. It left behind troubling paradoxes, cosmic mysteries that pointed to a missing chapter in our creation story. Imagine looking at opposite ends of the sky. The light from those two regions, separated by nearly 28 billion light-years today, has only just reached us. They have never been in contact. They have never had a chance to communicate, to exchange heat, to agree on a common temperature. And yet, when we measure the faint afterglow radiation from the Big Bang, the cosmic microwave background, we find that these disconnected regions are almost perfectly the same temperature, differing by only 1 part in 100,000. It's like finding two people on opposite sides of the Earth who have never met or spoken have somehow written the exact same novel word for word. This was the horizon problem, a riddle that suggested the universe knew something about itself that we did not. Another ghost was the shape of space itself. Our universe is extraordinarily unnervingly flat. On the grandest scales, it obeys the laws of Euclidean geometry you learned in school. Parallel lines remain parallel forever. If the density of matter and energy in the early cosmos had been just a fraction of a percent higher, gravity would have long since won the battle, pulling everything back into a cataclysmic big crunch. If it had been a fraction lower, the cosmos would have flown apart so fast that no stars or galaxies could have ever formed. Our existence balances on a gravitational knife edge of impossible precision, a fine-tuning so extreme it felt less like a coincidence and more like a clue. For decades, these were uncomfortable truths suggesting either a creator of unfathomable precision or a stroke of luck so absurd it bordered on the miraculous. Then in the 1980s, a new chapter was proposed, a radical prequel to the Big Bang we knew. This idea, called cosmic inflation, proposed that in its first fleeting moments, the universe underwent a period of incomprehensible expansion, driven by a bizarre form of energy inherent in the vacuum of space itself. For a sliver of a second, a moment shorter than it takes light to cross a single atom, the universe swelled in size by a factor of at least a trillion. It was not an explosion in space, but an explosion of space. The fabric of reality itself was stretched, pulled taut like an infinite drumskin in a fury of creation that defies all terrestrial analogy. This brief but titanic burst of growth was the cosmic starting gun. And with this one powerful idea, the ghost that haunted cosmology simply vanished. The horizon problem was solved. The regions we see on opposite sides of the sky were once in contact, nestled together in a tiny primordial patch, before inflation ripped them apart at superluminal speeds, stretching their shared properties across the heavens. They have the same temperature because they were born from the same quantum hearth. the flatness problem also evaporated. Any curvature the early universe might have possessed was stretched out into oblivion, just as the curve of a tiny balloon becomes imperceptibly flat when inflated to the size of the Earth. Inflation wasn't just an elegant solution, it felt like a necessary one. It explained the inexplicable, and its predictions, such as the specific pattern of tiny temperature fluctuations in the cosmic microwave background, have since been confirmed with stunning accuracy. We now believe inflation is a fundamental part of our cosmic history. But here in the very theory that so beautifully explains our own universe, we find the first mathematical doorway to countless others. The engine of this expansion was a theoretical energy field dubbed the inflating field, which permeated all of space. You can picture it as a vast landscape of potential energy like a mountain range. The state of the early universe was like a ball balanced at a very high unstable peak, a false vacuum. The Big Bang as we know it began when that ball started to roll down into a lower stable valley, the true vacuum of the universe we inhabit today. The immense potential energy it lost during that fall was converted into the torrent of matter and radiation that became our cosmos. The inferno of the Big Bang was the aftereffect of inflation ending. The profound reality-shattering question is this: what if the ball didn't stop rolling everywhere at the same time? Quantum mechanics, the strange but unassailable rulebook of the very small, tells us that the behavior of this field was not uniform. It was subject to quantum fluctuations, random jitters and uncertainties. In some regions of this vast inflating ocean of energy, the inflating field would have rolled down the hill, ending its reign, and allowing a universe like ours to blossom. A bubble of calm, stable space would form, filled with the embers of a Big Bang, and it would continue to expand at a more leisurely pace. But in other regions, quantum fluctuations could have kicked the field back up the hill, or kept it perched on a high plateau. In those places, the super-rapid exponential expansion would not stop. It would continue forever. This is the genesis of eternal inflation. It paints a picture not of a single finite event, but of an infinite ongoing process of creation. The inflating space between the bubbles, the false vacuum, expands so mind-bogglingly fast that it constantly generates new territory, creating more room for more quantum fluctuations to trigger the birth of new bubble universes. The process never ends. It is a cosmic cauldron, forever boiling, forever frothing with new worlds. Each bubble nucleates in this eternally expanding sea, a pocket universe with its own Big Bang, its own arrow of time, its own destiny. They are islands of matter and order in an infinite ocean of creative inflationary energy. From this perspective, our universe, our entire observable cosmos from the Andromeda galaxy to the most distant quasar, is just one bubble in an endless seething cosmic foam. Our Big Bang was not the beginning. It was just the moment inflation stopped here. It was a local event. Outside the walls of our bubble, the meta-universe, the multiverse, continues to inflate, continues to spawn new universes without end. This isn't speculation for its own sake. It is the logical, unavoidable consequence of combining our best theory of the universe's birth with the established laws of quantum mechanics. The theory that explains our home so perfectly seems to demand that our home is not unique. It forces us to confront a reality of staggering scale, where universes are born not once in a singular flash, but constantly like raindrops in an eternal storm. Eternal inflation gives us the engine, a mechanism for manufacturing an infinite number of universes. But it leaves open a critical question. What would those universes be like? Would they be sterile copies of our own, or could they be profoundly different? To answer that, we must turn to a completely different corner of theoretical physics, to a quest that began not with the cosmos, but with the atom. This is the search for a final theory, a single elegant framework that could unite the two great pillars of modern science, Einstein's general relativity, the law of the large, and quantum mechanics, the law of the small. This ambitious, all-encompassing dream is known as string theory. For nearly a century, these two theories have coexisted in a state of brilliant but frustrating disharmony. General relativity describes a smooth, curving fabric of space-time, while quantum mechanics depicts a frantic, pixelated world of probabilities and uncertainties. Where they meet in the heart of a black hole, or at the moment of the Big Bang, The mathematics of both theories break down, yielding nonsensical answers like infinite density and infinite energy. String theory proposes a radical solution. It asks us to reimagine the fundamental building blocks of reality. For all of history, we have thought of particles, electrons, photons, quarks as infinitesimal point zero-dimensional dots. String theory suggests this is wrong. At a level of reality far smaller than anything we can probe, these are not points at all. They are unimaginably tiny one-dimensional loops of vibrating energy. They are strings. In this new picture, the entire universe is a symphony. An electron is a string vibrating in one particular pattern. A photon is a string vibrating in another. A quark is a string with yet another distinct vibrational mode. The rich diversity of particles and forces we see from the light that allows you to see these words, to the gravity that holds you in your seat, are all just different notes played on these fundamental cosmic strings. It is a vision of ultimate elegance, a framework where all the complexity of the cosmos could emerge from one simple underlying entity. For this beautiful symphony to work, however, the theory makes an extraordinary demand. It requires that the universe does not have just the 3 dimensions of space and one of time that we experience. For the mathematics to be consistent, string theory requires a total of 10 spatial dimensions. So where are they? How can we live in a 10-dimensional universe and only perceive 3? The theory's answer is as ingenious as it is strange. The other 6 dimensions are there all around us, but they are curled up, compactified into intricate complex shapes on a scale so minuscule they are completely invisible to us. To grasp this, imagine an ant walking along a vast garden hose. From a great distance, the hose appears to be a one-dimensional line. The ant can only move forward or backward. But as you get closer, you realize there is a second dimension, the tiny circular path that wraps around the hose's circumference. The ant experiences this extra dimension, but to you, a giant observer far away, it is hidden. String theory proposes that at every single point in our familiar 3-dimensional space, there exists a tiny 6-dimensional shape, a complex geometric structure known as a Calabi-Yau manifold. And here in the geometry of these hidden dimensions lies the secret to the multiverse. According to the theory, there isn't just one way for these extra dimensions to be curled up. There are a staggering number of possible shapes. They can take a colossal number of ways to fold and twist this 6-dimensional space. The equations of string theory do not yield a single unique solution. Instead, they present a vast, sprawling landscape of possibilities. The number of these distinct mathematically consistent ways to compactify the extra dimensions is estimated to be at least 10 to the power of 500. That is a 1 followed by 500 zeros, a number so gargantuan it dwarfs the number of atoms in our entire observable universe. It is a number that for all practical purposes is infinite. This is the critical revelation. The precise shape of these curled-up dimensions is not merely a geometric curiosity, it is the master blueprint of physical law. The way the strings can vibrate the notes they are allowed to play is dictated by the geometry of the tiny space in which they exist. The shape of the Calabi-Yau manifold at a particular point in the landscape determines everything about the universe that would form from it. It sets the strength of gravity, the speed of light, the mass of an electron, the charge of a quark, the number of forces, even the number of large-scale dimensions that are allowed to unfurl. Every single constant of nature that makes our universe what it is that makes life possible is encoded in the intricate topology of these hidden dimensions. Each of the 10 to the 500 plus solutions in the string theory landscape corresponds to a different possible universe, a different vacuum state, with its own unique set of physical laws. We are living in just one of those vacuums, one stable valley, in an immeasurable mountain range of possibilities. In other valleys, the laws of physics would be completely alien. Imagine a universe where the electromagnetic force was weaker, a place where stars could never ignite, leaving the cosmos in eternal darkness. Imagine a universe where gravity was 1,000,000 times stronger, crushing all matter into black holes moments after its birth. Picture a universe with 4 large spatial dimensions instead of 3, where the inverse square law of gravity would fail, and stable planetary orbits would be impossible. The string theory landscape is a library of cosmic blueprints, and nearly all of them describe universes that are sterile, stillborn, or fleetingly chaotic. Now we can finally see the breathtaking convergence. We have two monumental yet completely independent lines of scientific inquiry. On one hand, eternal inflation born from cosmology gives us a physical mechanism for creating a literal infinity of bubble universes, a cosmic factory that never shuts down. On the other hand, string theory, born from the quest for a quantum theory of gravity, provides a landscape of possibilities, a stupendous menu of different physical laws that a universe could possess. When you put them together, a stunning and coherent picture of the multiverse emerges. The cosmic engine of eternal inflation creates the bubbles. The string theory landscape provides the die that is cast each time a new bubble is formed. As a new universe buds off from the eternally inflating sea, it undergoes a quantum transition, rolling down from the high-energy false vacuum into one of the countless stable valleys in the string theory landscape. Which valley it lands in is a matter of pure chance. The physical laws of that new universe are randomly selected from the near-infinite set of possibilities. In this grander cosmic lottery, the vast majority of universes would be duds, their fundamental constants incompatible with the formation of any kind of complexity, let alone life. They would be flashes in the dark, failed experiments in the cosmic laboratory. But with an infinite number of bubbles being created, it is not just possible, but inevitable that some bubbles would by sheer chance land in a valley like ours. A valley with the right constants, the right forces, the right dimensions to allow for stars, for planets, for chemistry, and ultimately for us. This marriage of creation and possibility resolves the deep mystery of our universe's fine-tuning. We are not the beneficiaries of an unbelievable cosmic coincidence. Our universe is not special. Instead, we simply find ourselves by necessity in one of the rare types of universes where observers can exist. We are a product of a selection effect, much like we shouldn't be surprised to find ourselves living on a planet with liquid water, because a planet without it could not have given rise to us in the first place. The laws of nature appear to be tailored for our existence, because we could not exist in a universe where they were not. We are the survivors of a cosmic game of chance played out on an infinite stage, and so we are left with this monumental vision, a vision of a cosmic foam, a seething, endless multiverse where our entire universe, all the galaxies we can ever hope to see, is but a single infinitesimal bubble. This is not a fanciful story. It is the destination we are led to by following the logic of our two most ambitious and far-reaching physical theories. They converge on this point, whispering to us that the reality we know is just a sliver of a much grander, much stranger, and much larger whole. But this profound picture, born from the purest mathematics, raises the most tantalizing and frustrating question of all. If these other worlds exist locked away in their own bubbles of space-time, separated from us by an impassable sea of eternal inflation, can we ever hope to find proof? Is there any way to look beyond the walls of our own cosmic bubble and catch a glimpse of the magnificent foam that lies beyond? And so we were left with two separate, almost mythic creations of the human mind. On one side stood eternal inflation, a self-perpetuating cosmic furnace. It was a wild, untamable engine endlessly churning out new pocket universes, each one born from a quantum hiccup in the fabric of space-time. This theory gave us a mechanism for creation, a process, a verb. It described how universes could be born again and again in a fractal bloom that would never ever cease. But it remained silent on a crucial point. It told us nothing about the nature of the children it spawned. Were they all just carbon copies of our own cosmos following the same rulebook of physics we have come to know, or was each one a unique and unpredictable creation? The theory on its own offered no definitive answer. It was a factory that shipped countless sealed boxes with no manifest to tell us what was inside. On the other side, a completely different beast string theory, born not from the dynamics of the Big Bang, but from the quest to unify the forces of nature to find the one elegant equation that governs everything. String theory offered us a static library of possibilities. It whispered of a 10-dimensional reality where the fundamental constants we hold so dear, like the charge of an electron or the strength of gravity, are not fixed values written in stone by some cosmic lawgiver. Instead, they are determined by the way those extra hidden dimensions are curled up and compacted into intricate invisible shapes. change the shape, the geometry of that compact space, and you change the laws of physics themselves. The theory didn't just allow for one way for these dimensions to fold, it presented a staggering, almost offensive number of possibilities, a number so large it defies all human comprehension, a one followed by 500 zeros. This is the infamous string theory landscape, a sort of celestial catalogue of every possible universe, each with its own unique physics, its own custom-built reality. For years, this landscape was seen as the theory's greatest weakness, a theory that predicts everything in a way predicts nothing. If our universe is just one of 10 to the 500 possibilities, how could we ever hope to find it in that bewildering mathematical jungle? It was a theory of everything that seemed to describe anywhere. For decades, these two monumental ideas existed in separate academic worlds. They were like two titans back to back staring into different voids. Inflation described a dynamic process of birth, the kinesis of the cosmos. String theory described a static menu of options, the potential of reality. One was the engine, the other was the blueprint library. Physicists working on one rarely interacted with those working on the other. They spoke different mathematical languages, tackled different problems, chased different horizons. The cosmos they described felt fractured, incomplete. We had an engine without a product specification, and a vast catalogue of products without a manufacturing plant. The disconnect was profound, a chasm running through the heart of physics. It seemed we were destined to be haunted by this duality, to possess two powerful keys that opened two entirely different locks. Until in a breathtaking moment of intellectual synthesis, a handful of brilliant minds realized something extraordinary. They weren't looking at two different locks at all. They realized the engine of inflation was the very mechanism that could bring the blueprints of string theory to life. This was the convergence, the grand unification of these two cosmic epics. The realization was that the violent quantum jitters of the inflaton field, the very process that sparks the birth of a new bubble universe, could provide just enough energy to knock reality from one configuration in the string landscape to another. Imagine the landscape not as a flat plain, but as a terrain of mountains and valleys. Each valley represents a stable possible universe, a set of physical laws where things can settle down. Our universe sits comfortably in one such valley, a low-energy state where stars and galaxies can form. But there are countless other valleys, some deeper, some shallower, each corresponding to a different folding of those extra dimensions, a different set of rules for reality. Eternal inflation then becomes the ultimate explorer of this landscape. As the inflaton field fluctuates, it doesn't just birth a new universe. It throws it randomly into one of these countless valleys. In one quantum leap, a new bubble springs into existence, and its fundamental properties, its very soul, are chosen by lottery from the string theory landscape. The universe next door might inflate into a valley where the electromagnetic force is 1,000,000 times stronger. The one after that might land in a configuration with 4 dimensions of space we could wander through. Another could be born into a state so hostile, so alien, that atoms themselves are a physical impossibility. Suddenly the two theories were not just compatible, they needed each other. They completed each other's stories, answering the questions the other could not. Eternal inflation was no longer a factory shipping mystery boxes. It was a cosmic assembly line churning out every single model listed in the vast, overwhelming catalogue of string theory. And the string landscape was no longer a frustrating abstract list of what-ifs. It was a tangible map of destinations, a field of real possibilities populated by an unstoppable physical process. This new combined vision was staggering. It painted a picture of a meta-reality, a multiverse of unimaginable scale and variety. We are floating in a foam of these bubble universes, and each bubble is a distinct world, a self-contained cosmos, separated from the others by an ever-expanding sea of inflationary energy. Within each bubble, an inhabitant would measure their own constants of nature, their own particle masses, their own cosmic destiny, and likely believe them to be the only ones possible. They would be entirely unaware of the sheer diversity rippling just beyond their cosmological horizon. Let yourself drift for a moment into this cosmic foam. Imagine a universe born into a valley where gravity is a repulsive force. There no planets or stars would ever clump together. Matter would fly apart in a thin, cold, featureless soup for eternity. Consciousness, as we understand it, could never arise in such a place. It is a stillborn reality, a silent, empty bubble. Now picture another where the strong nuclear force is just a few percent weaker. In this universe, protons and neutrons cannot bind together in atomic nuclei. The only element that could exist would be hydrogen. No carbon, no oxygen, no iron. No chemistry, no complexity, no life. The cosmos would be a simple, sterile expanse of lonely protons and electrons, a universe of gas without a single star to light it. Consider a bubble where the number of spatial dimensions is not 3 but 4. Here, the inverse square law of gravity would become an inverse cube law. Planetary orbits as we know them would be unstable. The delicate dance of suns and worlds would be impossible. Planets would either spiral into their stars or be flung into the void. The very structure of atoms would be different, potentially unstable. The predictable architecture of our reality would crumble. In another bubble, perhaps the cosmological constant, the energy of empty space that is causing our universe to accelerate its expansion, is 1,000 times larger. In that reality, this cosmic push would have been so overwhelming, so violent, that it would have ripped all matter apart before it ever had a chance to coalesce into the first galaxy, the first star, or the first planet. It would be a universe of fleeting, isolated particles, a frantic, lonely cosmos that tore itself to shreds moments after its birth. This cosmic foam, this grand multiverse, would be overwhelmingly, profoundly hostile to life. The vast, vast majority of these bubble universes would be sterile. They would be mathematical possibilities made real for an instant but dead on arrival. They would lack the specific, delicate, and seemingly arbitrary tuning of physical laws and constants that our own universe possesses. And this is where the story pivots, turning from the unimaginably vast back to the intimately familiar. It brings us face to face with one of the deepest and most controversial puzzles in all of science, the fine-tuning problem. The problem is this: when we look at the laws of our universe, the numbers that underpin reality, we find that they seem to be balanced on a knife's edge. If you change the strength of gravity by a minuscule amount, or tweak the mass of the neutron, or alter the energy of the vacuum, the whole intricate edifice of our cosmos comes crashing down. Life as we know it would be utterly impossible. For centuries, this apparent fine-tuning was seen by many as evidence of a cosmic design, a purpose, a creator. It felt too coincidental, too much like a setup. The universe, it seemed, was preordained to host us. But the marriage of eternal inflation and string theory offers a different, and for many physicists, a more compelling explanation. It introduces a concept that is as powerful as it is controversial: the anthropic principle. The principle in its modern scientific form is deceptively simple. It states that we should not be surprised to find ourselves living in a universe that is hospitable to our existence, because if it weren't, we wouldn't be here to observe it. It is an argument of selection bias. Imagine millions of people all playing the same lottery with only one grand prize winner. The winner might be tempted to see their victory as a miracle, as evidence of some special destiny or cosmic favour. They might ask, why out of all those millions of people did I win? But the answer is simple statistics. Someone had to win, and you're only asking the question because you are the one holding the winning ticket. The millions of losers aren't pondering the meaning of their failure. They've simply gone home. In the context of the multiverse, our universe is the winning lottery ticket. There are 10 to the 500 other bubble universes, the cosmic equivalent of losing tickets. They are sterile, empty, and devoid of observers. In those silent cosmoses, no one is marveling at the laws of physics because there is no one to marvel. The fact that we find ourselves in this particular bubble, with its just right properties for carbon-based life, is not a miracle demanding a supernatural explanation. It is a simple tautology. We could only have evolved and be here asking these questions in one of the very rare bubbles where the conditions were right. All the inhospitable universes go unobserved. This was a revolutionary paradigm-shifting idea. It transformed the fine-tuning problem from a question of why into a question of where. The question is no longer, why were the laws of physics so finely tuned? The question becomes, in which of the many types of universes do we expect to find ourselves living? The answer is, in one of the ones that can support life. It suggests that the fundamental constants we measure in our laboratories are not fundamental at all. They are environmental accidents' local bylaws. The strength of gravity in our corner of the multiverse is no more fundamental than the number of planets orbiting our sun or the atmospheric pressure at sea level on Earth. It's just a feature of our local cosmic geography. In another bubble far away in the cosmic foam, a different set of beings, if they exist, would be measuring their own constants, and perhaps wondering why their universe was so perfectly tuned for them. This anthropic reasoning makes many scientists deeply uncomfortable. It can feel like giving up, like a philosophical sleight of hand. Science is supposed to make definite testable predictions. A theory should explain why a constant has the value it does, not just say that the value is what it is because we are here to measure it. The criticism is potent if a theory can't be falsified. Is it even science? If we can never visit these other bubble universes, if we can never measure their different laws of physics, then how is this multiverse anything more than a grand unfalsifiable story? It's a valid and crucial concern, a line of tension that defines the frontier of physics today, and yet the power of this idea is undeniable. It takes what seemed like a series of bizarre, unrelated coincidences in our cosmic rulebook and reframes them as the consequence of a single, grander physical framework. It provides a potential naturalistic explanation for our existence within a much larger and far stranger reality. This was the turning point, the moment when the multiverse graduated from a philosophical speculation or a science fiction trope into a plausible physical consequence of our most advanced and promising theories of the cosmos. It was the midpoint of a conceptual revolution that is still unfolding a profound shift in our understanding of our place in the universe. We were no longer the centre of the solar system. We were no longer the centre of our galaxy. Now we had to confront the staggering possibility that our entire universe, everything we have ever seen or could ever hope to see, is just one bubble in an infinite cosmic ocean. One island of benign physics in an endless sea of sterile realities. This realization did not close the book on cosmology. It blew the book wide open, revealing chapters we never even knew existed. It forced us to ask a new, more audacious set of questions. If these other universes are real, could we ever find evidence of them? What would happen if two of these bubbles expanding in the foam were to collide? Could such a cataclysmic event have left a scar on our own cosmos, a faint bruise in the cosmic microwave background radiation, a ghost from another reality hiding in plain sight? And perhaps the most profound question of all, what does it mean for our beginning? If our universe is just one of many, then our Big Bang was not the beginning. It was merely a beginning, a local event in an eternal ongoing process. Our entire cosmic history from the first second to the distant cold future could be just a single fleeting chapter in a book that has no end. The search for answers would require us to push our observations and theories to their absolute limits to look for the faintest of whispers from a world beyond our own. And so we stand at the precipice of infinity, gazing out upon a sea of universes that stretches beyond all comprehension. We've journeyed from the singular spark of our own Big Bang to the breathtaking vision of a cosmic foam, a vast, ever-expanding meta-reality where our entire existence is but a single fragile bubble. The mathematics born from the very theories that describe our own cosmos with such stunning precision seem to demand this conclusion. They paint a picture so grand, so utterly complete, it feels like the final answer, the ultimate blueprint of reality itself. It's a vision that can fill you with a profound sense of connection to something truly eternal, a participant in a cosmic drama of unimaginable scale. But it is precisely here at the peak of this intellectual summit that the air grows thin and the ground beneath our feet becomes treacherous. For science is not merely a collection of beautiful ideas or elegant equations. It is a discipline forged in skepticism, a rigorous process of questioning, testing, and most importantly, doubting. The grandest theory, the most awe-inspiring vision holds no more water than a child's fantasy if it cannot be subjected to the cold, hard scrutiny of evidence. And as we stare into the shimmering abyss of the multiverse, a chorus of brilliant, cautious minds begins to ask the most dangerous question a scientist can pose. What if this beautiful idea isn't science at all? What if we have written a magnificent fiction, a new mythology for the 21st century and mistaken it for the truth? This is not a question of mathematical error or a flaw in the logic of inflation. No, the challenge is far deeper, far more fundamental. It strikes at the very heart of what we define science to be. For over a century, the demarcation line, the bright white stripe, separating science from philosophy, religion, and pseudoscience, has been a principle known as falsifiability. The concept is brutally simple. A theory is scientific only if it makes a prediction that can in principle be proven wrong. You must be able to conceive of an experiment, an observation that would force you to abandon your hypothesis. If your idea can explain every conceivable outcome if no possible discovery could ever contradict it, then it is not a robust theory. It is a faith. It is an infinitely flexible narrative, a fortress of logic so perfectly sealed that no arrow of evidence from the outside world can ever penetrate its walls. And this is the profound accusation levelled against the multiverse. How could you ever disprove the existence of other bubble universes? By their very definition, they lie outside our cosmic horizon, causally disconnected from us for all eternity. We can receive no light, no information from their shores. They are ghosts in the cosmic machine, their presence inferred only by the same equations that gave birth to our own reality. If we search the skies for evidence of a collision with another bubble, and find nothing, does that disprove the theory? Number proponents would simply argue that we are in a quieter, more isolated region of the multiverse, that the collisions are happening elsewhere far away. If our fundamental constants appear uniquely fine-tuned for life, the theory says that's just because we're in one of the rare bubbles where life could exist. If they didn't appear fine-tuned, the theory would be untroubled, for it predicts an infinite variety of constants across the foam. You begin to see the problem. It becomes a kind of philosophical black hole from which no empirical test can escape. The theory is so powerful, so all-encompassing, that it insulates itself from refutation. This places many physicists in an agonizing position. They have followed the trail of logic that began with Einstein's relativity, and the discovery of the expanding universe, a path that has led them step by step to this vertiginous conclusion. Yet at the final step, they find themselves in a realm where the trusted tools of their trade observation and experiment seem to crumble in their hands. They are like mariners who have used the trusted laws of navigation to sail to the edge of the known world, only to find an endless waterfall, a permanent cascade into the unknown, where all compasses fail and no map can be drawn. The scientific community is now deeply and sometimes bitterly divided. Is it time to redefine science itself, to accept that our ultimate theories might be so grand they can only be judged on their mathematical elegance and explanatory power? Or is it time to pull back from the brink, to admit we have strayed into metaphysics, and to declare the multiverse off-limits to science until a testable prediction can be found? This philosophical quandary, however, is only the beginning of the storm. As physicists delve deeper into the mathematics of eternal inflation, they unearthed a problem so bizarre and so intractable that it threatens to unravel the entire concept from the inside. It's a monster hiding in the infinities, a paradox known as the measure problem. And to understand it, you have to grapple with one of the most counterintuitive aspects of infinity itself. It breaks the very concept of probability. Imagine you have a bag with an infinite number of balls. Half of them are red and half are blue. You reach in and pull one out. What are the odds it's red? Your intuition screams 50%. But in an infinite set, that answer becomes meaningless. There isn't a total number of balls to divide by. You can create counting systems or measures that will give you any answer you like. For example, you could count 2 red balls for every 1 blue ball, and your measure would tell you the probability is 2/3. You could count 100 blues for every red, and the odds would plummet. With infinity, there is no single correct way to count. Now apply this dizzying paradox to the eternally inflating multiverse. The theory doesn't just predict many universes, it predicts an infinite number of them. Every possible outcome, every type of universe consistent with the laws of physics is not just created, but created an infinite number of times. So when we ask a simple predictive question like, what is the probability that our universe would have the value of the cosmological constant that we observe, we find ourselves in that infinite bag of balls. Eternal inflation in its purest form cannot give us an answer, because in an infinite cosmic foam, everything happens an infinite number of times. There are an infinite number of universes exactly like ours. There are an infinite number of universes where the only difference is that you chose a different breakfast this morning. There are an infinite number of universes made of pure gold, and an infinite number of universes where gravity is a repulsive force. Without a way to regulate these infinities to assign a sensible probability or measure to different types of outcomes, the theory loses all predictive power. A theory that predicts everything predicts nothing at all. It can't tell us why our universe looks the way it does, because it also predicts an infinite number of universes that look completely different. It's like a weather forecast that predicts sunshine, rain, snow hurricanes, and calm breezes, all for the same time and place. Technically, it will never be wrong, but it is completely and utterly useless. This is the measure problem, and it is the great unresolved crisis at the heart of modern cosmology. Physicists have proposed dozens of different ways to tame the infinities, to slice up the multiverse in a way that allows for sensible predictions. Some suggest we should measure by volume, giving more weight to the regions of space that expand the fastest. Others propose we should count along the timeline of a hypothetical observer, giving preference to universes that are more typical from a single point of view. But every proposed measure seems to have its own flaws, its own bizarre consequences. Some lead to terrifying conclusions like the Boltzmann brain paradox, which suggests that in an infinite universe it's overwhelmingly more probable for a single conscious brain to randomly fluctuate into existence out of the void, complete with false memories of a life like yours, than for an entire orderly universe like ours to form. If your measure predicts that you're almost certainly a random disembodied brain, then you can no longer trust your own observations of the universe, and the entire scientific enterprise collapses into solipsism. The fact that we have no objective agreed upon way to solve the measure problem has led many to believe it is a fatal flaw. They argue it's a sign that the theory of eternal inflation is at best incomplete, and at worst fundamentally wrong. It's a mathematical warning sign, a flashing red light on the dashboard of cosmology, telling us that our journey into infinity has led us into a logical paradox from which we may not be able to escape. This combination, the crisis of falsifiability and the mathematical morass of the measure problem, has fueled a powerful and articulate skeptical movement within the scientific community. These are not cranks or naysayers. They are some of the world's most respected physicists who look at the multiverse hypothesis and see a departure from the very principles that made science so successful. They hear echoes of ancient Greek philosophers arguing about the nature of the atom without any means of testing their ideas. They see a dangerous temptation to substitute mathematical elegance for empirical proof, to be seduced by a story that feels right, even if it remains forever beyond our grasp. The argument is a passionate one because it's about the soul of science itself. Is the goal to construct a theory that is logically possible and explains our own existence as a matter of chance? Or is the goal to construct a theory that makes unique testable predictions about the cosmos we can actually see? To these critics, the multiverse is an abdication of the scientist's responsibility. It's too easy. It uses an infinite, unobservable landscape to explain away the very features of our universe that are most puzzling and most in need of a unique physical explanation. Why is the Higgs boson the mass that it is? Why is the charge of an electron what it is? A traditional physicist would seek a deeper theory, a principle of symmetry, or a new law of nature that requires these values to be what they are. This is the dream of a final theory, a unique and elegant equation from which all the properties of our reality can be derived. The multiverse hypothesis, however, offers a different kind of answer. It says there is no deeper reason. These values are random accidents. We simply live in the bubble where the cosmic lottery produced a winning ticket for life. For many scientists, this isn't an explanation at all. It's the surrender of the search for one. It's like a detective faced with a baffling crime concluding that an infinite number of alternate realities exist, and this just happens to be the one where the butler did it. They worry that if younger generations of physicists embrace this kind of reasoning, the engine of scientific progress could stall. The relentless, often frustrating drive to explain the specific, peculiar features of our world could be replaced by a complacent shrug, a simple, that's just the way things are in our bubble. It risks transforming physics into a kind of statistical geography, merely cataloguing the properties of our local cosmic patch, without ever understanding the underlying laws that forged it. The debate is a clash of two different philosophies of science, two different visions of what a final theory should look like. One seeks a single, elegant and inevitable truth. The other accepts a vast, messy and contingent reality, where our universe is just one possibility among an infinity of others. One side accuses the other of giving up on the search for answers, while the other side accuses the first of a lack of imagination, of clinging to an outdated prejudice, that the universe must be uniquely tailored to our understanding. And so we are left suspended between a breathtaking vision and a profound intellectual crisis. The very theory that so beautifully explains the birth and structure of our own cosmos seems to lead us inexorably into a fog of untestable paradoxical infinities. We have built a magnificent theoretical ladder, but as we climb towards the highest rungs, we find they are not made of solid oak, but of mist and shadow. We are caught in a scientific catch-22. The multiverse seems to be a necessary consequence of our best-established physics, yet the multiverse itself seems to defy the very definition of physics as a testable science. It is a perfect logical prison, an idea so grand it might be true and so elusive it might forever remain an article of scientific faith rather than a statement of scientific fact. Is there any way out? Is there a hidden clue, a faint signal from beyond our cosmic shore that could turn this grand philosophy back into hard science? Or are we destined to stand here forever on the edge of our own bubble, able only to wonder about the ocean of reality that may lie eternally just beyond our sight? The challenge seems insurmountable, the silence from other universes deafening. But human ingenuity has a long history of finding ways to observe the unobservable, to measure the immeasurable. And even now, in the face of such daunting philosophical and mathematical barriers, a few bold scientists are beginning to search for a crack in the wall, a faint whisper in the cosmic static that could change everything. They are searching for a shadow, a scar, a fossil from a time before our own beginning, the last desperate hope for a message from the multiverse. And so we stand at the edge of an intellectual precipice. The theories we have explored are not mere mathematical phantoms. They are bold, sweeping predictions about the ultimate nature of reality. They paint a picture of a cosmos grander and more bizarre than any civilization has ever conceived a cosmic foam of infinite worlds. But a beautiful idea is not enough. Science demands more. It demands proof, a whisper of evidence, a single verifiable clue that can elevate this staggering concept from the realm of speculation into the world of accepted fact. The central agonizing challenge is one of perspective. How do you find evidence for a reality that exists by definition outside the boundaries of your own? If we are truly adrift in a bubble, an isolated island of space-time, we are prisoners of our own physics, captives of our own dimensions. We cannot build a ship to sail the cosmic foam. We cannot send a probe to pierce the membrane of our own existence. To search for another universe is to attempt the impossible, to see over a horizon that is everywhere and nowhere at once. Any hope we have lies not in looking out, but in looking back. Back to the single most important artifact in all of cosmology. Back to the faint lingering glow of our own universe's violent birth. We must turn our gaze to the cosmic microwave background. This is not simply a map of ancient light. It is the sacred text of creation, a celestial fossil imprinted with the echoes of the very first moments. It is our universe's baby picture, taken when it was a mere 380,000 years old, a turbulent, searing fog of plasma just beginning to cool and clear. Everywhere we look, this afterglow is astonishingly, almost perfectly uniform, a testament to the shared origin of all we see. But it is within its most subtle imperfections, the tiny millionth of a degree variations in temperature, that the entire story of cosmic structure is written. These minute fluctuations are the primordial seeds from which all the galaxies, the stars, and we ourselves would eventually grow. Theorists reasoned that if we inhabit a multiverse, if our universe has ever interacted with another, this ancient photograph is precisely where the scar would be found. Imagine two soap bubbles drifting slowly through the air. When they touch, they don't simply bounce off one another. For a moment, they press together their surfaces, deforming a flat circular boundary forming between them. Now scale that image up to a reality-altering cataclysm. A collision between two bubble universes would be the most energetic event conceivable, a clash of entire space-times. The energy unleashed at the point of contact would be unimaginable, a shockwave of gravitational and quantum force rippling through the fabric of both nascent realities. This cosmic impact would not be a gentle nudge. It would be a physical blow, a violent disruption that would leave a lasting mark, a permanent bruise on the infant cosmos. According to the models, this bruise would manifest as a distinct signature, indelibly printed upon the cosmic microwave background. It would appear as a vast circular pattern on the sky, a disk where the temperature and polarization of the ancient light deviate ever so slightly from the random noise around it. It would be the ghost of another world, its handprint left on our sky. Finding such a pattern would be the ultimate astronomical prize. It would be the first tangible piece of evidence that we're not alone, that our entire universe is but one component of a far greater whole. The search became one of the most ambitious quests in modern science. With instruments of breathtaking sensitivity like the WMAP satellite, and later the European Space Agency's Planck telescope, we began to scan this primordial light with unprecedented precision. For years, cosmologists and data scientists meticulously sifted through mountains of information, a deluge of petabytes from the sky. They were on a hunt for a ghost, a search for a pattern so subtle, so deeply buried in the statistical noise of the early universe, that finding it would be like trying to hear a single pin drop in the middle of a global thunderstorm. They developed sophisticated algorithms designed to scan the CMB map, searching for any statistically significant circular anomalies that could not be explained by known physics or simple chance. The algorithms churned, the data was processed and reprocessed, and then they found something strange, something deeply unsettling. In a swath of the southern celestial hemisphere, in the direction of the constellation, Eridanus lay an anomaly that had been hinted at for years but was now confirmed with chilling accuracy by the Planck data. It was a region of the sky far larger and far colder than it had any right to be. This was not a subtle deviation, it was a stark gaping anomaly. Known simply as the CMB cold spot, it is a blemish on the otherwise pristine face of our infant universe, a patch of sky spanning more than 1 billion light-years in diameter. Here the primordial photons are just a fraction colder than their surroundings, but on a cosmic scale that discrepancy is colossal. The probability of such a cold, vast region appearing by pure random chance in the standard model of cosmology is vanishingly small, less than 1%. Suddenly the multiverse was no longer a purely theoretical game. Here was a genuine mystery, a feature in our universe's oldest light that our best theories struggled to explain. The question was, electric. Could this be it? Could the cold spot be the bruise we had been looking for? Was this the definitive scar from a long-vanished collision with a neighbouring bubble universe billions of years ago? The excitement in the cosmological community was palpable. Teams around the world raced to test the hypothesis, running complex simulations of bubble collisions to see if the resulting imprint would match the precise temperature profile of the Eridanus anomaly. Some early models showed a tantalizing similarity. They predicted that a cosmic collision would create a cold spot surrounded by a subtle warm ring, and some analyses of the data suggested hints of such a structure might indeed be present. But science demands the exclusion of all other possibilities. And there was another far more mundane explanation. Perhaps the cold spot isn't an imprint on the CMB at all. Perhaps it is something between us and the CMB. This alternative theory proposed the existence of a supervoid, a truly colossal region of space almost entirely empty of matter. Such a void, perhaps the largest single structure in the known universe, would be an immense cosmic desert, billions of light-years across, containing far fewer galaxies, less dark matter, and less gas than average. As the ancient light from the CMB travels through this void on its journey to us, it would be subtly affected by a phenomenon known as the integrated Sachs-Wolf effect. The light enters the void, losing a bit of energy as it climbs out of the gravitational wells of the surrounding denser space. While inside the void, the universe continues to expand. By the time the light exits the void, the expansion has stretched the void itself, making the climb out of its gravitational influence less steep. The light therefore doesn't regain all the energy it lost on the way in. The net result is that photons passing through a supervoid appear to us as slightly colder, slightly less energetic. A hunt began not for bruises but for this hypothetical void. Astronomers used powerful telescopes to peer deep into that patch of sky, counting galaxies, mapping their distances and building a three-dimensional model of the cosmic web in the direction of the cold spot. Their findings were astounding. They discovered that a supervoid does in fact exist in that precise direction. It was a monumental discovery in its own right, a structure of such emptiness and scale that it challenges our models of cosmic formation. For many, this was case closed. The supervoid was the simple, elegant answer. It adhered to known physics and didn't require the invention of a whole new multiverse to explain the anomaly. But the story does not end there. As our measurements have become more precise, a lingering doubt remains. The supervoid, as vast as it is, may not be empty enough. Several detailed studies have concluded that this void can only account for a fraction of the observed coldness of the CMB spot. It can explain some of the temperature drop, perhaps 10 or 20%, but it struggles to explain the sheer intensity of the anomaly. The numbers don't quite add up. The cold spot remains too cold, too profound to be easily dismissed. And so, we're left in a state of exquisite scientific tension. The evidence is ambiguous, tantalizingly incomplete. The bruise hypothesis, the collision with another universe, has not been proven, but critically it has not been falsified either. The mystery of the Eridanus cold spot endures a giant cosmic question mark painted across our sky. And it is not our only clue. The search for evidence of the multiverse has expanded, looking for other more subtle signatures of cosmic impacts. Beyond just temperature, the light of the CMB has another property: polarization. We can think of this as the orientation of the light waves. Normally, the polarization across the sky should be random, but a violent collision with another universe could literally twist space-time, imparting a specific swirling pattern into the polarization of the light in the impact zone. This would be an even more definitive fingerprint than a temperature spot, a complex non-random signature that is exceptionally difficult to produce through any standard cosmological process. The latest generation of telescopes, both on the ground in places like the Atacama Desert and planned for future space missions, are being designed with an unprecedented ability to measure these subtle twists. They are sifting through the CMB, searching for these telltale vortices of light, another potential echo of a reality beyond our own. And there is yet another, even grander anomaly that gives cosmologists pause. When we look at the CMB on the largest possible scales, our universe appears strangely lopsided. The fluctuations, the hot and cold spots, are not distributed as randomly as our theories predict they should be. One hemisphere of the sky seems to have slightly more powerful fluctuations than the other. This axis of evil, as it was provocatively nicknamed, is a profound statistical anomaly. It hints that there is a preferred direction in the cosmos, a subtle asymmetry, baked into the fabric of creation itself. Standard inflationary cosmology says there should be no such direction. The universe on the grandest scale should be the same everywhere and in every direction. But what if it isn't? What if the cause of this asymmetry is external? Could this lopsidedness be the result of a lingering gravitational influence from a massive neighbouring bubble universe, which our own bubble is drifting towards or away from within, the greater cosmic foam? Perhaps our universe is not a perfect sphere, but is slightly warped, its contents subtly pulled to one side by the gravitational presence of something immense, unseen and nearby. Each of these clues, the stubborn cold spot, the search for polarized swirls, the baffling cosmic asymmetry, is on its own inconclusive. They could all eventually be explained by extensions of our current models, or perhaps by new physics we have yet to discover within our own universe. Statistical flukes, while improbable, are never impossible. But taken together, they begin to paint a suggestive picture. They are whispers from the darkness anomalies that stubbornly refuse to fit into our neat and tidy picture of a single, isolated cosmos. The search is a testament to human ingenuity and persistence. It is an act of cosmic archaeology, painstakingly brushing away layers of noise and foreground interference from our own galaxy, all in the hope of uncovering one authentic primordial artifact that could rewrite everything we know. The scientists engaged in this work are the ultimate explorers, charting the very limits of the observable. They work knowing that the signal they seek may not even exist. They may be chasing a ghost, a phantom born of beautiful but flawed mathematics. Yet the pull of the question is too strong to ignore. We have found strange footprints on the most distant shore we can see. We do not yet know what made them. They could be the result of a mundane tide, a simple trick of the light. Or they could be the first hint that just beyond the water's edge, past the horizon of our own reality, an entirely new continent awaits, teeming with possibilities we're only just beginning to comprehend. The hunt continues, pushing technology and theory to their absolute breaking points, driven by the most profound question we can possibly ask: are we and our entire universe truly all there is? And so we arrive at the threshold of our own reality. We have journeyed across the staggering architecture of eternal inflation, a cosmic engine that never truly stops, perpetually birthing new realms from the quantum froth of a parent vacuum. We have stared into the theoretical abyss of the string theory landscape, a mathematical vista with more possible worlds than there are atoms in our entire observable universe. We have sifted through the afterglow of our own creation, the cosmic microwave background, searching for the faintest bruise, the coldest spot, the telltale scar of a cosmic collision in the distant past. Through it all, a single monumental and perhaps terrifying idea has taken shape. An idea that reframes everything we thought we knew about our place in the cosmos. The idea that this universe, with its billions of galaxies, its intricate laws, its capacity for life, is not unique. That it is but one bubble adrift in a boundless, ever-expanding cosmic foam. This concept does more than simply expand the walls of our cosmic home. It dissolves them entirely. It suggests that the very laws of physics we have painstakingly uncovered, from the delicate dance of quantum mechanics to the grand celestial waltz of general relativity, may not be fundamental truths of existence. Instead, they could be local bylaws, the specific set of rules that happen to crystallize out of the searing energy when our particular bubble universe cooled. In another bubble, gravity might be a repulsive force flinging matter apart. In another, the electron might carry a different charge-making chemistry, as we know it utterly impossible. In yet another, there might be 4 spatial dimensions instead of 3, creating a reality so alien it defies our capacity for imagination. Our entire existence, the result of a 13.8 billion year cosmic story, could be just one possible outcome of an infinite cosmic lottery. This is a profound and for many a deeply unsettling realization. For millennia, we have looked to the heavens and seen ourselves at the center of the story. First, it was the Earth at the center of the cosmos, then the Sun, then our Milky Way galaxy as the sole island in an empty void. Each scientific revolution has served to decentralize humanity, to push us further from a position of cosmic privilege. The bubble universe hypothesis is perhaps the final step in this great Copernican demotion. It suggests that not only is our planet not special, our star not special, and our galaxy not special, but that our entire universe itself may be profoundly ordinary, an unremarkable member of an infinite cosmic family. Does this diminish us? Does it strip our existence of meaning and purpose? Or does it perhaps do the exact opposite? If there are infinite other universes where the constants of nature are just slightly different, rendering them sterile and empty, then our universe is not ordinary. It is extraordinarily lucky. Its precise tuning, the delicate balance of forces that allows stars to shine for billions of years, for heavy elements to be forged in their hearts, for planets to form, and for life to ultimately emerge, becomes not a mystery to be explained by a single overarching principle, but a winning ticket in a game of chance of unimaginable scale. Our existence becomes a testament to the sheer power of infinity. In an endless foam of possibilities, even the most improbable outcomes are not just possible, they are inevitable. We are the inevitable. This perspective recasts our scientific quest in a new light. Every discovery we make, every law we uncover, is a deciphering of our universe's unique genetic code. We are not learning the rules of the cosmos, but the specific rules of our cosmos. It is an act of profound self-discovery, on a universal scale, a mapping of our own pocket of reality. The question of why our universe is the way it is, a question that has haunted philosophers and physicists for centuries, is transformed. The answer may simply be because it could be, and because it is this way, we're here to ask the question. Elsewhere in other bubbles, with other laws, other beings, or perhaps no beings at all, are experiencing their own unique realities governed by their own local physics. We're all inhabitants of different islands in a vast metaversal ocean. But for now, this remains a staggering, beautiful and unproven idea. It is a grand narrative spun from the most advanced threads of theoretical physics, tantalizingly consistent with what we know, but hovering just beyond the reach of our experimental verification. The shadows and whispers we have detected, like the enigmatic cold spot, are not smoking guns. They are ghostly fingerprints that could be smudges. They are anomalous data points that fire the imagination but cannot yet form the bedrock of accepted fact. To cross the chasm from beautiful theory to physical reality, to prove that we are truly floating in a cosmic foam, we need more than whispers. We need a clear, unambiguous signal from beyond the edge of our own space-time. We need to find the seams of reality. The search for those seams is already underway, pushing our technology and our ingenuity to their absolute limits. One of our most promising tools is not one of sight, but of sound. We are building new ears to listen to the cosmos, to detect the faintest vibrations in the fabric of space-time itself, gravitational waves. Our current observatories like LIGO and Virgo have already opened a new window onto the universe, allowing us to hear the cataclysmic collisions of black holes and neutron stars. But to hear the echoes of the multiverse, we need something far more sensitive. We need to go to space. Future missions like the Laser Interferometer, Space Antenna or LISA will create a gravitational wave observatory of truly cosmic proportions. 3 spacecraft will fly in a triangular formation millions of kilometers apart, linked by laser beams of astonishing precision. This immense detector will be sensitive to the slow, gentle, long wavelength ripples in space-time that are completely invisible to ground-based instruments. It will be listening for the background hum of the universe, a primordial gravitational static left over from the very first moments of creation. And if our universe was born from the collision of 2 parent bubbles, or if it has been jostled by a neighbouring bubble in its cosmic infancy, the signature of that event would be imprinted upon this background hum. It wouldn't be uniform. The gravitational wave background would be slightly louder, slightly different in the direction of the cosmic impact. LISA would be listening for a sound that has been travelling towards us for 13.8 billion years, the sound of universes brushing against each other in the dark. It would be the most profound discovery in human history, a message not from a distant star but from a distant reality. Our other great hope lies in looking even more closely at the picture of our own cosmic birth, the cosmic microwave background. The images we have from missions like Planck are already masterpieces of precision, but the next generation of CMB telescopes will be even more powerful. They will map the sky with higher resolution, and crucially will be far more sensitive to a property of light called polarization. Polarization is the direction in which light waves oscillate, and it carries a wealth of information about the early universe. Specific patterns of polarization, known as B-modes, are considered a potential holy grail for cosmology. They are believed to be a direct signature of the primordial gravitational waves generated during the inflationary epoch itself. Confirming this specific type of primordial gravitational wave signal would be a monumental victory for inflationary theory, the engine that drives the entire multiverse concept. And if we can map these patterns across the entire sky with unprecedented accuracy, we might find subtle distortions. A collision with another bubble wouldn't just leave a cold spot, it could subtly twist and warp the polarization patterns in that region of the sky. It would be like finding a swirl in the otherwise smooth grain of a piece of wood, evidence of an ancient knot or disturbance. We would be seeing the gravitational aftershock of a trans-universal event fossilized in the first light of our cosmos. It would be an image of a wound, a scar, proving that our universe is not alone. The search also turns inward to the realm of the infinitesimally small. The Large Hadron Collider at CERN and future even more powerful particle accelerators are our probes into the high-energy physics that govern the birth of our universe. The bubble universe model emerges from theories like string theory that attempt to unify all the forces of nature. These theories often predict the existence of new particles and extra dimensions of space, but they only manifest at energies far beyond what we can currently achieve. By smashing particles together at ever-increasing speeds, we're recreating for a fleeting instant the conditions of the Big Bang. We're not looking to create a baby universe in a laboratory. The energies required for that are beyond comprehension. Instead, we are looking for the genetic markers of the multiverse. We are searching for evidence of the fundamental structure of reality that allows for the cosmic foam to exist. Finding evidence for supersymmetry or detecting the signature of extraspatial dimensions would not prove the existence of other bubbles, but it would provide powerful circumstantial evidence. It would show that the underlying physics of our world is consistent with the kind of framework that naturally leads to a multiverse. It would be like finding the specific gene in our universal DNA that codes for infinite cosmic reproduction. It is a long and arduous path sifting through the debris of subatomic collisions for clues to the ultimate structure of everything. And then there is the realm of pure thought of mathematics and theory. For every experimentalist building a new detector, there are teams of theoretical physicists exploring the landscape of possibility with pencil and paper, with supercomputers and imagination. They are the cartographers of the cosmos, drawing the maps that the explorers will follow. They wrestle with the paradoxes of black holes and the quantum nature of gravity, seeking a final theory, a theory of everything, that could describe the universe at its most fundamental level. If such a theory is ever found, it may tell us definitively whether the multiverse is an unavoidable consequence of the laws of nature or merely a fantastical mathematical dream. Their work is a testament to the power of the human mind to grapple with concepts far larger than itself, to build realities out of equations and see if one of them matches our own. So where does this leave us, you and I, on this tiny planet in this quiet corner of a single galaxy? It leaves us on the cusp of the greatest paradigm shift in the history of human thought. For our entire existence, we have defined ourselves by the boundaries of our world. We have looked up at a single shared sky. The bubble universe theory invites us to imagine that this sky is not a ceiling, but a membrane. A delicate shimmering surface of a single bubble in a sea of countless others. It suggests a cosmos more vast, more varied and more strange than we ever dared to conceive. This idea challenges us to reconsider the very meaning of words like everything and universe. It pushes our language, our mathematics and our philosophy to their breaking points. And whether it is ultimately proven true or false is in some ways secondary. The true power of this idea lies in its ability to expand our sense of wonder. The very act of contemplating it, of scientifically and rigorously pursuing it, stretches our minds and enriches our perspective. It forces us to confront the deepest questions of existence. Why is there something rather than nothing? Why these laws and not others? Why are we here? The quest for answers will continue. We will build our great observatories. We will listen for the whispers of gravitational waves echoing from the dawn of time. We will scrutinize the fading light of our own creation. We will delve deeper into the subatomic heart of matter. We may one day find that definitive proof, that cosmic scar, that unambiguous signal from another realm. Or we may find that our universe is all there is, a single magnificent and solitary creation. But we will never be the same for having asked the question. Look up at the night sky. See the stars not just as distant suns, but as atoms in a single cosmic bubble. Feel the ground beneath your feet, not as the bedrock of reality, but as the floor of one apartment in an infinite celestial city. The story of the cosmos is far from over. We may be living in the most exciting chapter yet, the moment we first realize the book itself might be endless. Our universe, our home, our everything may be just one beautiful, fleeting and exquisitely lucky bubble in an infinite, silent and ever-expanding cosmic foam.